everyone, I'm Karnika, and today we are exploring two crucial concepts in machine learning, bias and variance, along with their trade-off. We'll also unpack hypothesis space and inductive bias, providing a deeper understanding on how machine learning models learn and make predictions. Imagine you're training a machine learning model to predict house prices. You feed it a integral dataset for house price prediction, containing various features like house size, location, number of bedrooms, and so on. This model analyzes the data and learns the pattern to estimate selling price of a new house. However, the learning process isn't perfect. Two key errors arise: bias and variance. Bias. Consider of bias as an inherent prejudice in your model's predictions. For example, suppose a model that only considers house prices, ignoring the crucial factors like location. This leads to a systematic underestimation or overestimation in certain cases, introducing bias. Now, variance. This occurs when your model becomes overly sensitive to training data. For example, a model might capture every tiny detail, including random fluctuations in the data, leading to a model that performs well on training data but fails to generalize to unseen data. The bias-variance trade-off. Finding the sweet spot between these two errors have an interesting relationship. Reducing bias often leads to increased variance, and vice versa. It's like balancing on a tightrope. High bias, low variance, but inaccurate prediction due to oversimplification. High variance captures every detail, but fails to generalize to new data. The goal is to find a balance where errors are minimized. This allows for accurate and generalizable predictions. Now, let's explore hypothesis space. Imagine a vast universe containing all the possible models your machine learning algorithm could consider. Each model represents a unique hypothesis about how to predict the target variable, example, house prices. Based on input features, the type of model you choose, simple linear regression or a complex neural network, significantly shapes this space. Finding the optimal model within this vast space is like searching for a specific planet in the vast galaxy. This is where inductive bias comes in. It refers to the set of assumptions a model makes to generalize from training data to unseen data. These assumptions act like guiding light, helping the model to navigate the vast hypothesis space. Avoid getting stuck on irrelevant solutions. For example, a linear regression model assumes a linear relationship between features and the target variable. This assumption drastically reduces the hypothesis space, making it easier to find a good model. Different models come with inherent inductive biases. Choosing the right model with suitable assumptions for your specific data is crucial for effective machine learning. Recommender system. These systems use machine learning to suggest products or services you might be interested in. Understanding bias and variance is essential to ensure that these recommendations are accurate and avoid perpetuating unfair stereotypes. Medical diagnosis. Machine learning models can be used to analyze medical data and assist in early disease detection. Mitigating bias is crucial to avoid misdiagnosis, particularly for underrepresented groups in the training data. By understanding bias, variance, hypothesis space, and inductive bias, you gain a deeper grasp of how machine learning models learn and make predictions. This knowledge empowers you to critically evaluate these models and ensure that they are reliable and generalizable. The field of machine learning is constantly evolving. As you dwell deeper, you'll encounter more advanced concepts and techniques. Remember, the key is to stay curious and keep exploring this fascinating domain. I'll see you in the next video.